then P must be equal to Pj for some, excuse me, j in 1 to 2. Okay, right? It has to be one of them they're primes in our finite list of primes, right? Thus, Pj divides M, and Pj divides P1, the product of the primes, right? And what else do we know? Well, M minus the product of the primes, right, is equal to 1. Thus, Pj divides 1. And that is not possible, right? That is a contradiction. So apparently we cannot have finitely many primes. Now, there are a number of proofs of the infinity of various kinds of primes that kind of follow this general template of suppose there's finitely many and like come up with a specific construction algebraically and then prove some absurdity follows from that. If, you know, so not everything can be proved in this way, but there's a number of things that can be proved in this way. In Jones and Jones, he actually has the details, like, so here's some results. There exist infinitely many primes of form 4q plus 3. There exist infinitely many primes of form 4q plus 1. And then sort of the ultimate version of this sort of thing was by Dirichlet in 1837. He said that if A and B were coprime, then there exist infinitely many primes of form AQ plus B. All right. So the proof on the proof that there are infinitely primes of the form 4q plus 3 is in Jones and Jones, and essentially what he does, essentially what they do to look at that one, is something similar to the proof I have here, but instead they look, for this one, basically look at something that's like formed like this: M is equal to 4, the product of your finite number of primes of that form, right, minus 1, and then they're able to find a contradiction similar to the style of Euclid's theorem. All right. So I think that was kind of neat.
Math world is very, for the longest time, everyone explained Terry Tao as stating this theorem, or the one. I feel like that's just because
What's that?
like, if you just listen to things, you would think Terry Tao did this.
Oh.
And that is not what he proved. He proved something much different.
Well, I think Tao has improved the state of the art on some of the things I'm about to mention.
Yeah, but I'm
Yeah.
just saying, like, that was the theory that most, like, if you look at this thing on Jimmy Fallon, it makes it seem like he created.
Oh. Well, I think that's what happens when you have popular accounts that are trying to like explain things mathematicians have known for millennia.
Yeah.
It's easy to get lost in the idea that the mathematician on the show is creating the thing that civilized folks have known for some time. So here's a couple of results that are pretty neat. The nth prime, all right, Pn, is less than or equal to 2 to the 2 to the n minus 1 for all n greater than or equal 1. All right? 2 to the 2 to the n minus 1. Corollary 2.8 says that pi of x is greater than or equal to the floor function of the log base 2, which is Lg, of the log base 2, Lg of x, closed floor function, plus 1. All right, now I need to explain to you what pi of x is. All right. Pi of x is the number of primes less than or equal to x. All right, so like, for example, pi of 2 is equal to 1. Pi of 2.2 is equal to 1. Pi of 3 is equal to 2 because 2 and 3 are prime, right? Pi of 10, what are the primes up to 10? 2, 3, 5, 7, so 4. 4, all right. So these are 2 baby steps in bounding the growth, or basically these put bounds on how many primes you can have. This says that the nth prime has to be found before then, all right? And this says that you have to have at least this many primes found.
That's upper and lower.
It's upper and lower. Now these are both very loose in both directions. So, for example, the example that they give, if you look at x equals 10 to the 9th gives, this estimate here gives pi of x is greater than or equal to 5. But as a point of order, a point of explicit calculation, pi of x is it's approximately 5 times 10 to the 7th. So yeah, it's a little bit off. Let me put put that in more common language. If you look at the integers up to 1 billion, there are 50 million primes. About 50 million primes in the first billion numbers. You know, as opposed to that which says there, hey, there's more than 5. Okay.
It's like when the teachers have put out that jar of jelly beans. Students like it's at least 12.
That's funny. I need to do that next year for the onboard thing.
Oh, that's great.
Yeah, I need to do something like that. Prime number theorem. This was conjectured by Gauss in 1793. And what he said was that pi of x is, it's approximately Li of x, which is defined to be the integral from 2 to x of dt over the natural log of t. All right, or you could argue it this way, pi of x over ln n of x goes to 1 as x goes to infinity. This is the so-called prime number theorem I mentioned, A1. This was conjectured by Gauss, 1793, which he wasn't that old at that point. I mean, he wrote the discussion of arithmetic when he was like 21. That was 1801. I mean, what was he, like a teenager? Anyway, this was proved apparently by Poussin and Hadamard in like 1896. I'm surprised. So that gives you kind of an account of how many primes. It's a much tighter account than the others. Now, I mentioned that I said something along the lines of Goldbach's conjecture and the twin prime conjecture are the same. Incorrect. These are different things. Goldbach's conjecture is that every integer larger than 4 is the sum of 2 primes. As far as I know, this is open. The twin prime conjecture says that there are infinitely many prime pairs of the form p comma p plus 2, right? So that's the Goldbach conjecture, that's the twin prime conjecture. Both of which there have been various state-of-the-art advances on that I am not aware of. While we're on this list of fun things about things that are prime or estimates. Now, by the way, these things I just told you, these are what do you think, algebraic number theory or analytic number theory? What are we looking at here? Very much analytic number theory. That's right. distance between primes, huh?
Yeah. It was 3:46.
Yes, but I started late. So I must finish this, this section. What's that?
That's fine.
Are you okay?
Yeah. I'm just gonna leave the math lab open after this.
So Fermat and Mersenne primes. I don't have much. I won't start the modular stuff today. I'm not crazy, but I do want to wrap up my fun facts about primes. I am close to the end. So Fermat number F sub n is equal to 2 to the 2 to the n plus 1. All right. Now, Fermat conjectured that these are primes. And he had good reason to think so, because if you start listing them, you got yourself a 3, a 5, 17, 257, 65,537, and these are indeed prime. However, F5 is 2 to the 2 to the 5, right, plus 1. And it turns out that that's equal to 641 times 6,700,014, 417. Who figured this out? Euler in 1732. So maybe Fermat didn't live to. I forget what was Fermat. When was Fermat dead? He's probably dead before we saw this, but yeah, he'd been long gone by the time this was found. And
Oh man, he didn't see America before.
and here's the interesting thing. Not only is that not a prime, we haven't found any further Fermat numbers which are primes past that. And they have looked. I don't think it's been proved, but no more. Now, this is interesting because in 1801, Gauss showed K-gon, in other words, a regular-sided K-polygon, can be constructed. Is compass ruler constructible? If and only if K happens to be equal to 2 to some power E times the product of Fermat primes. So there's some weird connection between these Fermat numbers and the possible constructibility of K-gons, which is just, it is weird. Although I want to say Gauss constructed the 17-gon using compass and rule. Gauss did some really annoying feats of classical. There were problems that were unsolved in Euclidean geometry for a couple millennia that Gauss just said, here, solve. And then the Mersenne numbers. I'm skipping all this. There are various theorems on these things. I'm just skipping all that. I just want to kind of give you the big picture of this, okay? So MP is equal to 2 to the P minus 1, right, for P prime. This is a Mersenne number. So, like, here's a list of some of the first ones. 3, 7, 31, 127. These are all prime, right? However, when you get to the 11, M11, it's equal to 2047, and that happens to be the product of 23 and 89. So it's composite. And unlike the story of Fermat numbers, Mersenne numbers, they're primes. As of 1996, when Jones and Jones was published, there were 35 Mersenne primes found. I'm curious what the current. I have not had a chance to look up the, to consult the internet and find out what the current number is, right? And so that brings me to my final topic for today, which is primality testing. And the difficulty of finding prime factorizations, of course, for large numbers is the thing that our encryption systems rest on, it turns out. So there's basically two results that I'll share with you. And so the one, super useful, an integer n greater than 1 is composite if and only if it is divisible by some prime p less than or equal to the square root of n. Let's see if we can improve too many things here in this part of the chapter, but this is worth us talking about. So, okay, so let's go this way. If p is less than or equal to the square root of n, and p divides n, right? Then what? Well, let's see here. How about this? P is less than square root of n, which is less than n, right? So p is not equal to n. And if p is not equal to n, and p is a divisor of n, that means n is composite. Times something else, a, right? Right. In other words, n is composite, right? Now the other direction, if n is equal to ab, right? Then if a is greater than the square root of n and b is greater than the square root of n, we're in trouble. ab is equal to square root of n is greater than, right? It's greater than square root of n times square root of n, which is equal to n, but n is equal to ab, right? Is greater than n? That's a contradiction, right? So clearly, suppose a is less than or equal to the square root of n without loss of generality, right? I mean, one or the other of them is. Then what can you say? We know n is equal to ab, right? But if you look at this here, right? a is an integer, right? A greater than 1 is integer, right? Well, it implies that there exists a prime factor of a, right? That was one of our basic things. Every integer has at least one prime factor. Now, a may or may not be prime. I don't know, but certainly there exists p prime with p dividing a, right? But what did we one of our parts in our divisibility theorem was that if P is a divisor of A, remember that P, the absolute value of P is less than the absolute value of A. But here, that just becomes P is less than A. Well, less than or equal to, right? It's less than or equal to the square root of n. But if P is a prime divisor of, if P is a prime divisor of A, it's also a prime divisor of AB. So we have now found a prime divisor of AB, which is n, which is less than the square root of n, which is what we're trying to prove. And of course, this is super helpful if you're looking for, is a number prime or not. It suffices to like check divisibility of the numbers up to the square root. Now, of course, like, I'm trying to think of a good example, like, $242. That's got, well, 2 is a divisor, right? See, I constructed this as 2 times 11 squared, right? 11 squared is 121. 121 times 2 is that. I'm trying to think of how this plays out. So, like, 242 square root is what? Like,
What's the closest one? 169.
225 is 15 squared. So it's like 16 maybe. So, but we'd find it though. We'd find 2 and we'd also find 11. But we didn't have to find the 11. That's the thing, is this doesn't quite illustrate what I was trying to get at. Like, I don't think you have to find all of the primes searching up to the square root, but you have to find at least one of them, is the thing, My last thing for today was the sieve of, I can't say it, Eratosthenes. Have you ever seen this before? Now, there are the state of the art in finding primes and stuff like that. I don't even begin to know. And it's not even in Jones and Jones, really. They just kind of like say stuff is known. But this is something you could teach to elementary school children, and this has been known since antiquity. It's pretty simple, really. So here it goes. First of all, just list the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Note to self, make a handout for this if you ever teach it again. All right. I mean, this could keep going. All right, so here's the deal. You circle, so cross out the 1, 1's not prime. Circle the first prime you find, 2. Aha, 2 is a prime, right? Then you get to cross out all multiples of 2. So a smart person would have said, I'm just going to write down odd numbers because, like, so obviously there's some labor-saving moves. I'm just showing you the sort of most rudimentary, unthinking, just then you do 3, yeah. So 3 is the next. Then we cross out multiples of 3. So we lose that 9, 15, 21, 27, 33, 39, 45, all gone. All right, so what's our next prime is 5. And let's see, we lose 25. I missed that earlier, and then Professor Giles and Professor Parker, they made fun of me. But I remember that. Revenge is a dish best served cold. Let's see here. 5, 7 is the next. And I think 7, we have to cross out like 49 in my list, pretty much it. And then 11's the next. I don't know if we've already, I think we already got 22 and 33 for other reasons. All right, so yeah, 13. I think we've already got the multiples of 26 for other reasons. 17. And I think we've already gotten the multiples of 17 for other reasons. 19. 23. 29. 31. 37. 41. 43. And 47. If I haven't forgotten a multiple.
Yeah, there's a lot of these twin primes.
So, oh yeah, there's a few sets of twins in there. And so this is the Sieve of Eratosthenes. I'm not spelling that right. Anyway. Which is a method that I think would be fun to like waste the time of elementary school children with, right? Like, do this for numbers up to 1,000. Like, that's a pretty serious arithmetic exercise, isn't it? Anyway, so next time we shall start with the congruence material. Sorry if I'm off my schedule.